Hi and good evening, Balaji. Please tell me if you are able to see my screen and if my audio is audible. If you are not able
Uh,
to,
Sir,
ha,
your
ha,
screen is not visible. Just share your screen.
is it now visible?
Yeah, it's visible now.
Okay, okay, thanks. So I'll just wait for one more minute and then we can start. Okay. Um,
Yes, yes, yes. Before that, I have one doubt. Can I ask now?
yeah,
Some
sure.
assignment problem is related to assignment problem only. I have a doubt. Can it be
Okay.
explained?
Yeah, I can explain, but based on the rules, like I cannot actually help with assignment
You
problems.
can't
So
explain. No, just give the hint how to proceed with that. That is the thing I need. I don't want to have some complete explanation, the answer. Give the procedure to proceed with that so that I can do it.
okay, you show the problem, then I will just see what I can tell because
Uh,
like
yeah,
obviously
that's
I cannot.
not a problem. If you can tell, you tell. Otherwise, no need. I'll proceed then. Like
Sure,
tomorrow
sure,
is
sure. Okay, okay, okay. You just show.
the third question in the assignment, week number 8. I will share you the screen.
Yeah, yeah. You can share your screen.
1 minute. I'm unable to share it. Yes, able to see that this problem.
Yeah, but your screen is blank. Okay.
Now it's okay, visible.
Yeah, yeah. Go ahead.
Yeah, this one only. Third problem. What they're telling, two converters are connected in parallel, and they have given equal duty cycle, means 50% duty cycle with 1 kilohertz of switching frequency. So, with operational switches as the average value of current switch into decimal places. So this one only.
Okay.
So in
Okay,
this
okay.
one, yeah, yeah,
Just hang on a second. I'll just read the problem.
yeah, yeah.
Figure shows two buck converters connected in parallel. Okay, the common input DC voltage for the converters as a value of 100 volts. The converters are inductors of identical value. Load resistance is 1 ohms. Okay. Capacitor voltage has negligible ripple. Both converters operated in CCM. Switching frequency is 1 kilohertz. Okay, okay. Assuming that the converters share the load equally, average load current of switch S1. Okay. So in this, what is your doubt? Like at what point are you getting stuck?
No, in this one, I am getting I'm able to find out the load current, like inductor current, the current flowing through the inductor.
So you're able to find out what is IL1 and IL2, right?
Yeah.
Okay. Then
So
it's pretty straightforward then after that.
no question is, it will be equally divided, right?
Yeah, so if you assume that the switches S1 and S2 are identical, right? So
Yeah.
then IS1 and IS2 must be same,
Okay.
correct?
That is right. That is why I'm having a doubt. So it will be the
Yeah,
total
yeah. So you
total
assume
current will
that
be
both the
divided.
switches are identical switches, I mean ideal switches.
Mm-hmm.
So once you know what is the individual inductor current,
Mm.
you can just directly find out what is the device current also, right? That is S1 or S2.
Yeah, yeah.
Yeah, so it's yeah, you're right. It's you can
Okay.
assume both the devices to be identical and proceed.
Okay then. Thank you.
So can I start sharing my screen now? Okay. Okay, so I hope my screen is visible now. We will just start. So let me turn on my camera. I don't know. Yeah, it works. So, okay, so I hope my screen is visible. In case the visibility goes off, please feel free to unmute and tell. Um, just hang on a second. I'll just connect my charger. Then we'll just start off. Okay, so I think we can start now. Good evening and welcome again to the problem solving session for week number 8. So in this week, I guess you dealt with two main types of converters, that is your forward converter and flyback converter. And as you might have studied in the lecture slides as well, the forward converter is kind of an isolated buck converter where you derive the topology from the conventional non-isolated buck converter by introducing some isolation stage in it, right? And the same thing is applicable for flyback as well, wherein you derive the flyback converter by giving or by inducing a isolation stage. So we will not be going into the theoretical aspects of that. We will jump right ahead into the problems. Okay. I'll just take my pen. Okay. Okay, so we'll go into the problems. The first problem is a flyback converter is supplied from a battery of 25 volts. The voltage across the load, that is V naught, is 25 volts and is drawing a current of 1 ampere. So V naught is given, I naught is given. Flyback converter switch is operating at 25 kilohertz and a duty ratio of 0.6. So your D is 0.6 and the Fs or the switching frequency is 25 kilohertz. Note that in the question also and in the diagram as well, they have not specified what is your N, that is the turns ratio. What should be the minimum voltage withstanding capability of the switch S in volts? Okay. So point is, what is the voltage that appears across the switch when the switch is in the off state, obviously. Okay. So in this problem, the circuit diagram is given, and in case the circuit diagram is not given, I strongly recommend that you draw the circuit in your rough sheet or whatever it is. Okay, and that will give you much more clarity of thought. Okay, so sorry for that, I just lost connection. Okay, so as I was telling, please do draw the circuit diagram. So this is a basic question. So this is your flyback converter, and this is something that's already given in the problem, right? And the information that you have is Vi is 25 volts, V naught is also 25, and the duty cycle is, I guess, 0.6, right? Okay. So your duty cycle is 0.6. Since you know that in a flyback converter, the input-output relation is governed something similar to a buck converter, right? So you will know that V naught, as we tell it, V naught over V in is equal to N times D over 1 minus D, correct? So if you solve this equation, you get what is N, right? You will get what is N, right? And also they have given, I mean, the question that is asked is what is the voltage withstanding capability of the switch is. So you will know that the voltage across the switch is going to be the voltage that appears when the switch is in the off state, right? So in case you don't know, the value is actually what? Vi plus V naught over N. But no need to worry in case you don't know what you can do is you draw the circuit of the flyback converter and draw its equivalent state or equivalent circuit when the converter is into off state, correct? So this is your 25 volts input, okay, or let me call it VI for now. Yeah. So this is 25 volts, and then you have your VP, and then you have your device, okay. So this is your device, and this is the voltage that you need to find out, SVS, okay. So obviously you will know that VP is going to be the reflected voltage of whatever is there in the output, correct? So during the 1 minus D period, you will know that this diode is forward biased. Therefore, what you get is a voltage of 25 volts or V naught at the secondary terminals, or the secondary at the secondary winding terminals. This is then transferred to the primary side, and therefore VP would be something like Vs over N, that is V naught over N, correct? Therefore, what you will understand is, okay, so let me write this as V secondary, this is V primary. Okay, so V primary will be V secondary over N or V naught over N. Therefore, your switch voltage or Vs, correct, or VQs is given in the lecture slides. It is going to be what? Simply Vi minus Vp, right? So this is going to be something like Vi minus of, you know that the dot polarity is kind of in opposing mode for flyback converter. Therefore, Vs is equal to Vi minus Vp or Vi plus V naught over N, right? So this is your blocking voltage across the device, right? So you will find out what is N from this relation, and from the relation that the blocking voltage across the device is Vi plus V naught over N, you can get what is Vs. Okay, so this is the way to go ahead, go about this problem. Okay, so we will go to the solution that's already given, right? So D is 0.6, so you substitute that in this equation and you get what is N, okay? And since we just derived that when the diode is conducting and the switch is off, so obviously you should remember one thing or note one thing, that if they ask what is the voltage withstanding capability of any device, that means that that particular device is in the off state. Okay, if they ask for the diode, it means that the diode is off, correct? Only then it will block some voltage, right? Or when it is conducting, obviously the voltage across the device is almost zero, correct? So the voltage across the switch means the switch is in the off state, that is the converter is in its 1 minus D period or 1 minus DTS interval, correct? So from this you get that the blocking voltage across the device is Vi plus V naught over N. Okay, just by applying KVL you get that. So it turns out to be around 62.5 volts. Okay, so this is a pretty simple problem, so I'm just marching ahead. If you have any doubts, you can write in the chat box, or of course you can unmute and interrupt. Okay, so we will go ahead with the next problem if this is fine. Okay, so below figure shows a schematic circuit of multi-winding flyback DC-DC converter. What are the values of output voltages V01 and V02 respectively at a given duty ratio of 0.6? Okay, so D is given and the input is given as 24 volts. So from this, it should be quite clear to you that since your V0 is n times V into D by 1 minus D, you can just substitute for what is V01 and V02. Okay, individually, right? So this is the multi-winding flyback converter. That is, in the primary side, you have one turn. In the secondary side, you have one part of it with 2 turns, the other part with 3 turns. Okay. So irrespective of whatever is the turn number, you always note that all the properties of a transformer that you studied are always valid over here as well. Okay. Okay. So we'll keep that aside for the next part of the problem. But however, the output voltage individually is going to be what? just you need to include the turns ratio of the corresponding secondary windings. Okay, so for instance, VO1 is going to be VO1 is equal to n times d by 1 minus d into Vin, correct? And same is applicable for VO2 as well. This is just a direct substitution of the formula. So from that you get that VO1 and VO2 are going to be 72 volts and 108 volts respectively. Okay, that is this is directly derived from the input output relation for a flyback converter. Okay, so I guess this is pretty straightforward. If you don't have any doubts, we will go to the next part of the problem, which is more interesting. Okay. Okay, so this was just a linear relation between the input and output. Now the next part is, what is the peak voltage stress across the switch in the circuit of question 2? So what is the peak voltage across the switch? So this is your switch over here, correct? So this is your switch. They are asking what is the peak voltage stress across the device. Okay, so this was something that was asked in the first problem as well. So what is the blocking voltage across this device, correct? What should be the minimum voltage extending capability of across the device? And over there, we saw that the switch voltage Vs, or let me call it Vq, is equal to what? Vi minus Vp, correct? This is your Vp. Just by KVL, you get Vq is equal to Vi, which is 25 volts over here, minus Vp. And later on, it turned out that Vp is equal to what? Minus V naught over N. Therefore, Vq is equal to Vi plus V naught over N. So this is something we saw in the previous problem as well. So this is a blocking voltage across that device. So in this problem also, they are asking pretty much the same question, but over here you have multi windings in the secondary. Okay, that is, you have multiple windings in the secondary. In that case, what is the blocking voltage across the device? So anyone has any idea how do we proceed about? In case you get the answer, you can of course unmute and tell. Okay, but point is, we will go back to the circuit once again. So in this circuit, we need to find out what is Vp, right? So if we find out what is Vp, we know that Vq is equal to what? Vi minus Vp. Okay, so we just need to find out what is Vp in this problem. Okay. Okay, so let me take the help of a new slide for this. And then the slide. Okay. Okay, so let me go to full screen. Oh, sorry. Okay, so this is what is asked, and this is the circuit diagram, as you know. Okay, so now you note that for any transformer, right? So what you tell is the volt per turn should be same, correct? So for any transformer, V1 over N1 should be equal to V2 over N2 should be equal to V3 over N3, and so on. Irrespective of the number of windings it has, this relation should hold. That is, volt per turn is balanced. So this is one point, and the second point is what is known as MMF balance, correct? MMF balance, or you can call it flux balance, whatever it is. So MMF balance should be maintained. That is, let's say that your conventional current direction in each of the windings is something like this. This is I1, okay, and of course current enters the dot, therefore I2, and this is what is I3. Okay, so what you will see is, or what you should see in steady state, ideally if you don't want the transformer to saturate, is N1 I1 should be equal to N2 I2 plus N3 I3. Correct? That is MMF in the primary should be equal to the total MMF in the secondary. Okay. So this is something that you will all obviously know. That is N1 I1 should be equal to N2 I2 plus N3 I3. Okay. Now, if you one more thing that you would know is obviously the volt ampere balance. Volt ampere balance. Correct? Or let me tell, V1 I1 should be equal to what? V2 I2 plus V3 I3. So this is something that is always, I'm sorry. So V1 I1 should be equal to V2 I2 and that's equal to V3 I3. So let me place this. Okay. Okay. So this is something that is always maintained in a transformer, right? So with this information, you can understand that whatever is the reflected voltage in the primary side Vp at any point of time, Vp will be equal to what? Or V primary will be called it. V primary may be equal to, let's call this V1, V2 and V3 for convenience. So your V1 over here, this is V2 and this is V3. So you will know that, you should know that V1 is equal to what? V1 will always be equal to minus of, because the dot polarity is opposite, minus of V2 divided by N2, correct? Or I can also write V1 is equal to minus of V3 divided by N3. Okay, so because if all of these criteria for a transformer are balanced or satisfied, then this holds, right? That is V1 is equal to minus V2 over N2 or minus V3 over N3. Correct? Therefore, you can understand, coming back to the problem, that what is the voltage stress across a switch in circuit of question 2. So you will know that Vp over here can be given by minus of VO1 over 2 or minus of VO2 over 3, right? The 2 is the turns number, 3 is the turns number here. So from this, you can find out what is Vp, correct? So we will use that particular relation and therefore you will end up with VO1 is actually 72 volts and N is 2. Therefore, Vp will be what? Therefore, over here, Vp is equal to minus 72 over 2. That is minus 36 volts. Or you can also write this should be minus 108 over 3. This again minus 36. Right? Minus 108 was VO2. VO2 was 108 volts. So you get Vp is equal to minus 36. Therefore, your switch blocking voltage or VQ is what? Vi plus Vp. Correct? So Vi is 24 and Vp is 36. Vi plus mod Vp. Okay? And this gives you 72 volts. I'm sorry, not 72. How much is this? This is going to give you 60 volts. Okay. So this is how it should be done, but in the answer key, it's the values have been summed up. That is, this is Vi and this is VO1 over N1 and this is VO2 over N2. Okay. And that is why they are getting 96 volts is the answer.
Excuse me. Can you press that hide at the bottom of the screen in the presentation?
Oh, okay, okay. Just a second. Yeah, so Okay. So in the answer key, it is given as 96 volts. That is, they have summed up Vi plus V1 V1 by N1 plus V02 by N2. But you can understand that if the transformer principle holds, then this should be true, right? That is, Vp should be what? Vp should be minus V2 by N2 or minus V3 by N3. Okay, that is from transformer principle that you get. And among the given options also, the answer that we got, that is 60 volts, is not there. Therefore, in that case, you can very well choose 96 volts. That is, they have summed up over here. But actually, you understand that the correct approach would be to do like this. Okay, because always your volt second balance across your inductor needs to be maintained. Okay, you keep that in mind, and therefore you just find out what is the primary voltage. Again, a pretty simple problem, right? That is just you find out what is Vp. You know that the switch voltage is going to be Vq is Vi minus Vp. Okay, so just find out what is Vp. Vp turns out to be minus V0 over N. Okay, and just you sum it up, you get what is Vq. Okay. Um, So next question is again a continuation. What is the peak inverse voltage stress across the diode D1 of the circuit shown in question 2? So the previous question was about the stress across the switch. Now the question is, what is the voltage across this diode? Okay. Or if you take the polarity, it should be something like this. Okay. What is the voltage across the diode? So again, what you need to do is you just need to transfer your primary to the secondary side over here. You will understand that the diode voltage Vd, right? So in this side you have V0. So in this side you have V0, and in this side you have the V secondary. Correct? This is your V secondary 1, let me call it. So you understand that the diode voltage is actually what? Diode voltage is going to be V0 minus V secondary 1, correct? Simply the voltage across the anode to cathode, or sorry, cathode to anode, is going to be V0 minus V secondary 1. Okay, so you know that V0 1 is actually how much? 72 volts. But what is, okay, so before I go to the specifics, so what is V secondary 1? V secondary is actually the reflected voltage from the primary onto the secondary side. So V0 minus V secondary 1 will be what? N1 into Vp, or V0 minus N1 into V in, right? So this is your voltage across the diode. So since the dot polarity is opposite, you will of course write V0 plus, correct? Because the dot polarity is opposite over here. Okay, so V0 plus N1 into Vp, or V0 plus N1 into V in. Okay, so this is what is done over here as well. Yeah, so when the switch is on, that is when this device is on, when the MOSFET is on or the BJT is on, what happens is the switch is shorted. Therefore, across Vp you get Vi, and you take it to the other side of the transformer, you will end up with NVI over here, and this is your V0. Therefore, the voltage is going to be V0 minus of minus NVI. Correct? Yeah. So that is how you do it. So you already know what is Vn, you know what is N, and V01 is also given in V01 was also calculated in one of the previous problems. So in this problem, we calculated what is VO1, what is VO2. Then we calculated what is the voltage across the device Q, and we calculated what is the voltage across the diode. Okay, so all these four were calculated in the past 3 questions. Okay. Okay, so next question is pretty simple. Forward converter is rate from dash buck boost, buck boost, choke, or SEPIC. SEPIC full form, just for information, SEPIC is single embedded point we will of course study about this in the coming lectures. Okay. So anyway, so forward converter is derived from what? Forward converter is obviously derived from buck converter, right? It's an isolated buck converter, isolated form of buck converter is actually forward converter, right? Okay. So in a flyback converter, the ratio of average input to output current is 10/3. That is, what is given as input to output current or I in over I naught is equal to 10/3. While operating with a duty ratio of D equal to 0.6. What is the ratio of maximum voltage seen by diode to the maximum voltage seen by primary side switch? So you try to understand. It would be better if you use the circuit again, correct? So just give me a second. I'll just use the figure for better understanding. So okay. So forget about that about the turns ratio here. Let's say this is 1:2. Okay, so instead of this figure, just hang on a second. I'll just use. Yeah. So shown over here is flyback converter. Neglect the values of the input and output that is given, but what we require is what is the ratio of maximum voltage seen by diode to maximum voltage seen by primary side switch? That is, what is the voltage of the diode divided by what is the voltage of the device Q or Vs. So we just solved this in the previous problems. We saw that Vs is actually what? Vs is V in plus V naught over N. That is V in plus the reflected voltage in the primary side. And what is the diode? Diode voltage is going to be V naught. That is the output voltage and the reflected voltage in the secondary. Correct? Reflected voltage in the secondary. So the reflected voltage will be what? V in over N, correct? So V naught plus V in over N, right? So you understand that the switch blocking voltage is V in plus V naught by N and VD is V naught plus V in by N. So just write over here VD by VQ is equal to what? V naught plus V in over N divided by V in plus V naught over N. See, in this problem, they have not given anything related to V naught. V naught is not given. V in is not given. Just they have given the ratio of input to output current and D is given. Okay. Okay. So we will try to get more sense out of this. That is V naught plus V in by N can be written as N V naught plus V in divided by N whole divided by N V in plus V naught divided by N. Correct? So sorry, so just we just made a small error over here. That is your that is your diode voltage will be what? Reflected voltage in the secondary is V naught plus NV in. So V naught plus NV in divided by V in plus V naught over N. So just try to simplify this. So V naught plus NV in divided by, again you take N to the top. So V in plus V naught divided by N. So you see that this and this term gets cancelled and you're ending up with N. That is the ratio of the maximum voltage seen by diode to maximum voltage seen by primary side is actually what? It is nothing but just N. You just need to find out what is N, and that is your answer. Okay, ratio of voltage seen by diode with respect to voltage seen by primary side switch. So it's just solve the values and you get that the ratio is actually N, or the turns number. Okay, now we will go back to the problem. That is I in by I naught is 10 by 3. Correct. So let me take a new slide. So we just saw that VD by VQ is equal to N. This is on one side. And what is given is I in over I naught is actually what? 10 by 3. Therefore, since you know that V naught I naught is equal to V in I in. Correct. Therefore, V naught over V in is equal to I in over I naught. So I in over I naught is nothing but V naught over V in. V naught over V in is 10 by 3. Correct. So in a flyback converter, you know that V naught over V in is going to be simply N D over 1 minus D, which is equal to 10 over 3. And D is given as 0.6. Therefore, you can find out what is N. Correct. D is equal to 0.6 given in the problem itself. D is equal to 0.6. Got it right? Another simple problem. Just the ratio between voltage seen by diode and switch needs to be solved, and you end up with N. Therefore, it is also. Let me check if my screen is visible or not. Okay. So, and you see that. Yeah. So you see that I in over I naught is equal to V naught over V in by power balance, and therefore you can solve for what is N, and that is actually your answer. Okay. Yeah. So the same thing is mentioned in the solutions as well. That is, this is the output input relation, and you get what is N from this. Your ratio is nothing but N, that is equal to 20 over 9. Okay. Okay. So we'll move on to the next problem. So for steady state analysis purpose, the operational conditions and power stage parameters of the flyback converter are Vs is 24 volts, magnetizing inductance Lm is equal to 160 microhenry, N2 is to N1 is 0.5, filter capacitance N2 is to N1 means the output side turns with or the secondary side turns with respect to the primary number of turns is 0.5. Filter capacitance is 400 microfarad, R is 2.5 ohms. Switching time period is 20 microseconds or 50 kilohertz, right? Duty ratio D is 0.4. Determine the average magnetizing current of the converter. Okay. So magnetizing current means you have a magnetizing inductance branch in the primary side. Okay. So what is that particular current, right? So, and they are asking us to determine the average magnetizing current. Okay. So you understand that this is a normal flyback converter, right? So generally what you have, okay. So generally what you have is you have a diode over here, correct? So this will come over here, and over here you have a MOSFET or a BJT or BJT. Okay. So this is your general flyback converter that you are aware of. But what we have also studied in the lecture slides is that, right? So before we go ahead, since they have asked something related to magnetizing current, we need to first draw the circuit diagram including this. Okay, that will give us more clarity. Okay, I strongly recommend you guys to draw the equivalent circuit before you proceed to solve. Okay, so this is your general flyback converter, but since they have given something related to magnetizing current, you also need to include the magnetizing branch, right? So you know that since a transformer can be written or it can be drawn something like this. Okay. However, incorporating its non-idealities and all, right, you will know that the transformer can be drawn, including its leakage and core and its magnetizing component, correct? So, yeah, including its magnetizing component, you can draw the transformer to be something like this. Okay, correct. So this is your equivalent circuit of a transformer, or if I neglect the non-idealities, that is the leakage and the winding resistances, what you are going to end up with is including the core component. Okay, so what you will end up with is something like this. Okay, no losses, just the magnetizing inductance part alone is there. Now, if I neglect the core loss, correct? If I neglect the core loss or the RC as we call it, the core loss component, what you see is that you have a shunt branch across the primary, correct? There is a shunt branch across the primary, and this is what we call as a magnetizing inductance. So magnetizing inductance kind of defines what is the flux that is required to actually magnetize the transformer. That is, for instance, in the BH curve, you know that while you expect to operate in this kind of a fashion, initially you need to magnetize it, right? Magnetize it, and then you see that there is this residual magnetism. So this particular component, that is this residual component, or whatever is the flux required to achieve this residual component, that we represent it in terms of the magnetizing inductance. Okay, so we need to include that over here because in the question they are asking what is the magnetizing current of the converter. So you include that, and hence you end up with something like this. That is, there is a shunt component across the primary winding, and that is what we are calling it as LM. Okay, so this is the same flyback converter, just that this let me erase all of the ink in this slide. Okay, yeah, so this is the same flyback converter, just that this transformer has been modified slightly to include the magnetizing inductance. Now we need to find out what is the average current through LM. So, so we need to find out what is the average current through LM. Right? So just a second. Okay. Okay. So we'll go back to the equations of the circuit that we already know, circuit operation. You know that during 0 to DTS period, okay, so during the 0 to DTS period, diode is off, right? The diode blocks a certain voltage, okay, and hence what would happen? The switch is on. Therefore, you end up with VLM, or let me call it, okay, so VLM, that is the primary side voltage, is equal to exactly Vs, as is the convention over here. So VLM is equal to Vs during 0 to DTS period. Since voltage is positive across the inductor, this is equal to what? LM into DIM by dt. Okay. Since voltage is positive, you will see that IM rises up. Correct? DIdt is voltage, or DIdt is positive. Therefore, I increases. Therefore, you see that your IM is increasing from some value to peak value. Correct? So this is how the current would increase. Correct? This is during 0 to DTS period. And you will obviously know that during this period, this capacitor is actually supplying to the load. Therefore, your IC is equal to minus I naught or minus IA over here. This is the convention. Okay. So you know that IC is equal to minus IA during 0 to DTS period. During this 1 minus DTS period or DTS to TS period, this switch is off. This switch is off and the diode turns on. Correct. Obviously, the inductor current cannot go to zero abruptly. It cannot jump to zero. So what would happen is that the inductor is now going to freewheel. Okay, the inductor would now freewheel. And what is the path for freewheeling? You will understand that the inductor would freewheel something like this. Correct? Inductor would freewheel something like this through the primary side winding itself. Therefore, whatever is the current over here actually gets reflected to the secondary side. Therefore, I can tell that the diode current is going to be Im over N, correct? That is your um, inductor current that is freewheeling that gets reflected to the secondary side. Okay, therefore, this current is going to be Im over N, right? Im is the magnetizing inductance current. So this is your Im over N, and therefore you can understand that Ic is equal to what? Im over N minus Ia. Correct? This is just KCL. Okay. So this is the operation of the magnetizing inductance. That is, first you have the I appearing across the magnetizing inductance, and during the DTS to TS period, this is your VA, that is the output voltage. Output voltage gets reflected back to the primary side, and therefore the voltage across the magnetizing winding is going to be what? VLM is equal to what? VLM is equal to your V primary, which is equal to minus VA over N. Okay, since the voltage is negative, that is minus VA over N is negative, therefore you see that LDI dt is negative, therefore Im falls. That is why you see the Im current is falling over here. Correct? So you see that during the 0 to DTS period, the voltage is Vs, the inductor current rises up, and then during the 1 minus DTS period, the voltage is minus V0 over N, therefore the inductor current falls. Okay, so this is the operation that we are all aware of already, right? So now what we can do is, there is a reason we have taken up this capacitor. What we can do is we can apply capacitor charge balance. So capacitor charge balance is something that you have already studied. Okay, just got logged out. Just hang on a second. I'll just. Okay, so capacitor charge balance is something you guys have studied already, right? That is during the DTS period, you see that the capacitor supplies the output voltage, therefore the current is minus Ia, right? So this is minus Ia, and during the 1 minus DTS period, the primary current is reflected to the secondary side, therefore the capacitor current is going to be from KCL Im by N minus Ia. Okay, so by capacitor charge balance, you see the capacitor waveform over here, correct? So what you end up is the total charge should be equalized. Therefore, this area over here, right? This area over here should be equal to this area. That is the positive area and negative area should be same. Okay, that is why. So that is why what is done over here is d times Ia is equal to 1 minus d times Im by N minus Ia. Correct? So from this relation, you end up with Im is equal to NIA divided by 1 minus D. Okay. So this is your relation for capacitor for the magnetizing current of the inductor. That is Im is equal to N times Ia by 1 minus D. So now from the given data, you get what is VA. Therefore, you get what is Ia. Okay. And therefore, you get what is Im. Okay, so this is just the procedure. I will go through the procedure once again, but let me take a new slide over here, and Yeah, so I copy these and paste it over here. Okay, so yeah, so from the equivalent diagrams, you are able to understand that during the first interval, IC is equal to what? IC is equal to simply minus IA. Okay, during the first interval. And during the second interval, what is IC? IC is equal to Im by n minus IA. Correct? I have written capital IM and capital IA to indicate the average values. Okay, even though the graph is falling something like this, we are taking the average. Okay, therefore Im by n minus Ia is a DC quantity or an average number or a fixed quantity. Therefore, we can assume it is something like this, somewhere in the middle. Okay. Therefore, what you do is you apply capacitor charge balance over here. That is, the area over here and area over here should be same. Correct? Therefore, D times Im is equal to what? 1 minus D times Im by n minus Ia. That is just the area, right? Positive area is equal to negative area. From this, you get what is Im in terms of Ia. It turns out that Im is equal to Ia into n by 1 minus D. Ia is the output current. Okay. So this is, let me just pause over here. Is this point clear? How Im is obtained? Can anyone unmute and tell if this is not clear? I can explain it once again. Okay. How Im is obtained? That is from capacitor charge balance. If you guys need a minute, you can just I'll just wait here for 1 minute. You can just go through this. That is, during the DTS period, you see what is IC. During 1 minus D period, what is IC? Correct? Draw the IC graph, and you obviously understand that during the DTS period, the capacitor is discharging to the load, therefore the current is negative. And during the 1 minus D period, the capacitor is charging, therefore the current is positive. Okay, and what we are doing is we are applying capacitor charge balance, that is the area of IC into T should be same, right? That is DTS into IA is equal to Im by n minus Ia into 1 minus DTS. So TS are cancelled anyway, and from this you get what is Im. You get what is Im in terms of Ia. Ia is your output current. So you know that V0 is equal to NV in into D by 1 minus D. From this, find out what is V0, and you know that I0 is equal to V0 over R. Therefore, what is I0, or this is your Ia. From this, you find out what is Im. Im is equal to Im into N by 1 minus D. Okay. Is this point clear? Is this problem clear to you guys? Any doubts so far in this? Okay, so let me just open the chat box. I don't know why it's not open. Okay, fine. Okay, so I hope this problem is clear to you guys. This is one of the tricky problems, right? Okay, so I'll just hang on over here. I'll just have some water and we can just resume in around 2-3 minutes. Okay. In the meantime, you just go through this problem. You try to understand what is being done in this problem, and we will take it up from here for the remaining problems. Okay. Yeah. So again, for this problem, I will recommend that you always draw the circuit diagram, because without circuit diagram, this problem cannot be solved. Okay. A whole lot of information is given, that is LM, the filter capacitance and all of these are not required, obviously, as you can understand, right? So Yeah, so try to go through this problem and we can continue in around 3-4 minutes time. Okay. Yeah, so we'll just continue from here. Yeah, so what we were seeing is regarding this problem wherein we had to find out the average value of the magnetizing inductor current and the relation we were able to get from capacitor charge balance at the output side, right? That is, we wrote what was the capacitor current during DTS period, that is minus IA, and during 1 minus DTS period, that is Im by N minus IA, and we kind of drew the capacitor current waveform as it is drawn in the right hand side of your screen, right? And we found out the area during the positive side and negative side, and it turns out that Im is equal to I naught into N divided by 1 minus D. Okay. It is also given from the problem. The information is given regarding what is N. So N is given, correct? So N is given and D is given and Vs is also given. Therefore, VA or the output voltage is 8 volts. So IA is what? IA is V naught by R, that is 8 by 2.5, that is 3.2 amperes. That is your IA. Once you know what is your IA, you can get Im or the magnetizing inductor current, that is N times IA by 1 minus D. You end up with 2.667 amperes. Okay. You just need to understand how this particular relation is coming. Okay, and that is coming from capacitor charge balance. Okay, just equalize the areas in both cases and you get the answer. Okay, if you have any doubts, please do type in the comment section or the chat section. Okay, chat box, you can pick it up. Hope this problem is clear to you, how this magnetizing inductor current is coming. This was, I think, the trickiest problem of the lot. We will go ahead with the next problem now. Okay, so flyback converter is derived from dash. Again, a simple problem, buck boost, choke or pick. You know that flyback is the isolated version of buck boost converter. Okay, so this is flyback converter. Yeah, so before I go ahead, let me check the comment section. Okay. For designing of flyback for designing of flyback converter, sourcing power from 20-volt input voltage source and supplying it to 10 ohms load. Excuse me. For designing of flyback converter, sourcing power from 20-volt input voltage source and supplying it to a 10 ohm load with duty ratio equal to 0.4 and turns ratio and secondary by N primary equal to 4. Find the load voltage V naught and the minimum value of inductance LP seen from the primary side. So there is a flyback converter. Let's break it down to parts. And Vs is given or Vin is given. So Vin is given. Okay. It is applying it to a 10 ohms load. So RL is given. So R is given. And duty ratio is given, of course. And the turns ratio N secondary by N primary is 4. That is N is equal to 4. Find the load voltage V naught. Okay. And the minimum value of inductance LP from the primary side. So first part is pretty simple. V naught is equal to what? N into D by 1 minus D into V in. Right? This is for a flyback converter. So N is given, D is given, and V in is given. Therefore, you get what is V naught. So first part is pretty simple. And what is the minimum value of inductance from the primary side? So we need to find out what is the minimum value of inductance. But they have helped us with what? Switching frequency is 100 kilohertz. Current ripple through the transistor when it is conducting is less than 10% of input average current. So current ripple or the delta IL should be less than 10% of what? 10% of the average input current or I in. Okay. So I in can be found out and delta IL should be less than 10% of that. You know that V is equal to L into delta IL by whatever is the dt. Okay, so from this you need to find out what is L. So again, the relation is pretty simple. V is equal to L di by dt. You just need to know what is di. You need to know what is dt. Okay, and you get the answer. Simple, right? Just the question seems to be bigger, but it is actually a simple problem. Okay, so we'll just solve the first part for now. You know that in a flyback converter, V naught is equal to ND into V in by 1 minus D. Straightforward relation. You know what is N, you know what is D, and V in is also given. Therefore, you end up with 53.33. So luckily for us, only one of the options has 53.33. Therefore, you end up with the answer, but we also need to understand or learn how to get this particular value of LP. Okay. Okay, so we will go ahead with the next part of the problem, that is what is LP, right? So before we proceed, let me take a new slide. Okay, so before we proceed, we just saw that V is equal to L di by dt. Therefore, I can get L as V into dt by di. Okay, this is the answer. I need to know what value of V to put, what value of dt, and what is the value of di. And you get what is L. Correct? Okay, so now we will go back to the basics of a flyback converter. In the last problem as well, we were seeing that, yeah. So in this problem as well, we are seeing that, let me just copy these two figures. Okay. So in this problem, we saw that during the DTS period, VL is equal to Vs, and during the 1 minus D period, during the 1 minus DTS period, there is a reflected voltage from the secondary onto the primary side. Therefore, VL is equal to what? VL is equal to minus VA over N. Correct? If I take this as a polarity. Agree? That is VL is positive during the DTS period. Therefore, current increases, I increases, and VL is negative during the 1 minus D period. Therefore, the current decreases. Okay, and this is something that we saw extensively in the previous problem as well. Okay, so we can take either of these relationships to find out what is L. Okay, so we know that, let's say we take this particular interval, therefore we know that V is equal to L dA over dt. Therefore, during the DTS period, VL is actually Vs or the V in. Okay, Vs is equal to L into di can be written as delta I divided by the period is DTS. Therefore, you end up with L is equal to Vs into DTS by delta I. Okay, or you can also do during this particular phase or this particular interval, wherein you end up with again VL is equal to L into di by dt. So this is a rising interval and this is a falling interval, obviously, correct? So VL is equal to minus V naught by N is equal to L delta di by, so let me, yeah, L into minus delta I, because the current is falling, I have taken minus delta I divided by the time period is 1 minus D period. So 1 minus DTS. Therefore, L is equal to what? V naught into 1 minus DTS divided by delta I. I can bring Ti to the lower side. I can bring Ts to the bottom side or the denominator side, and I can write Fs. Similarly, over here also I can write it as Fs. So this is the value of the inductor required. Correct? that is Vs into d by delta I into Fs, or V naught into 1 minus d by delta I into Fs. So both of these are correct. You can do either way, right? Whatever you wish. Okay. So this is a relation to get what is L. Okay. Now we will go back to the problem. We just found out what is V naught, correct? So let me erase some of the ink over. Okay, so not able to erase. So let me take a new slide. So we found out what is V naught. V naught is what? N d by 1 minus d into Vn. We found out what is V naught. Therefore, your I naught is simply V naught over R, correct? And you know that V naught by V in is equal to I in over I naught, and that is equal to N d by 1 minus d. Therefore, from this relation, you can get what is I in. Correct? You can get what is I in. So if you get what is I in, they have given in the problem that if you go back to the problem, current ripple through the transistor when it is conducting is 10% of or less than 10% of average input current. So your delta I that we require, delta I is simply less than or equal to 10% or 0.1 into I in. Correct? So this is your delta IL. So you will find out what is delta IL from this. Once you know what is delta IL, you just substitute in the equation that we just derived. L is equal to Vs into d by delta I into Fs. Vs into d by delta I into Fs. Okay, you get what is L. Simple, right? Just find out what is V naught, find out what is I naught, I in. Given in the problem that delta IL is 10% of I in, therefore you just substitute in the relation for L. And how did we find out L? The relation, that is, we just analyze the flyback converter during when the flyback converter is conducting, that is when the switch is on and the switch is off. So when the switch is on, voltage across the inductor is input voltage, that is Vs, and when the switch is off, voltage is a reflected voltage from the secondary, that is minus V naught over N. Okay. So this is why you would have seen that anyway the inductor current is something like this. Correct? This is your inductor current, and this particular region, that is this particular region is your dTs period. This particular region is your 1 minus dTs period, and the inductor current is rising because the VL is positive. That is, the inductor voltage is positive. That is, the slope would be Vs by L, and this slope would be what? Minus V naught by N over L. Okay, this is falling slope because it's a negative voltage. Correct? So this is your inductor current, obviously. So you can take either convention as your means for deriving what is your inductor, and peak to peak ripple is delta IL. Okay. Okay. So I hope this problem is clear to you guys. That is how we derived what is L, and we just substituted all the values. So you do that, substitute the values, that is I naught turns out to be 5.3 amperes, IN is determined, and from that you got what is delta I. So IN is 14.21 amperes. Therefore, delta I is 10% of that, which is 1.421 ampere. From that, you get that inductor voltage is, as we just derived, during DT period, inductor voltage is Vn, L into delta I by dTs. So from that, you get what is L, 56.3 microhenries. Okay. Yeah, so in the problem as well, I think, yeah, 56.3 microhenry. Okay. So I hope this problem is clear to you. It has been elaborately explained as to how we derived L. In the previous problem, we saw similarly, by applying capacitor charge balance, how we derived IM, that is the current through the inductor. In this problem, we saw how to derive LM, right? How do we derive LM? How do we derive IM? So all of this was explained using capacitor charge balance and just from the inductor volt current relation directly. Okay, so let me check if there are any doubts in the chat box, or else we can proceed. Okay, so yeah, I'll just proceed. What is the minimum voltage withstanding capacity required for the primary power semiconductor switch in a forward converter, which utilizes a lossless flux reset topology, is supplied from a 72-volt battery, operates at a duty ratio of 0.4 and a frequency of 25 kilohertz with a load voltage of 15 volts and load current of 1 ampere. So everything is given, that is input voltage, output voltage, and duty is given, and the frequency is given, and the load current is also given. However, N is not given. Okay. So what is the voltage withstanding capacity required for the primary power semiconductor? Okay. So from the lecture slides, you would have understood that this has an auxiliary winding or a third winding, or we call this as the demagnetizing winding, right? So this is known as the demagnetizing winding. Okay. Okay. So you can understand that when the switch is on, obviously the operation is similar to like a buck converter that you would have already studied. However, when this switch is off, right, that is you turn off this device, correct? So then what is the voltage that appears across this device? Vs. So just by applying KVL, you will understand that your Vs is simply V in plus the reflected voltage, correct? V in plus Vp. Okay. So V in is given as 72. You need to find out what is Vp. Okay. So once you find out what is Vp, Vs is simply V in plus Vp. Just by applying KVL, you get this. Correct? Okay. Okay. So in the problem, they have given you what is D, that is 0.4. And they have also given what is V naught, that is 15 volt. Okay. So from this, you can get what is N, right? Because you know that, I'm sorry. You know that V naught over V in. So this, of course, is a forward converter. Therefore, the V naught over V in is going to be simply V naught over V in is going to be simply N into D. Okay. Therefore, you get what is N. Correct. So, yeah. So 72 divided by D is 0.4. So from that you can get what is N. And once you get what is N, you will know that Vp is simply what? Vp is V naught over N. That is the reflected voltage in the primary side. Okay. So by this you get what is Vs. However, you would have studied from the lecture slides itself. That is, when you have a demagnetizing winding or a tertiary winding, the voltage across the switch is now going to be V in plus again V in. That is, the switch now needs to block 2 times V in. Correct? So from this, you can understand that the blocking voltage is going to be 2 times 72 volts. Therefore, straightforward, you get the answer is 144. Okay. So this is something that has been explained in the lecture slides also. That is, when you have the tertiary winding or the demagnetizing winding, the blocking voltage across the device kind of is 2 times VIN. Okay. Yeah. So the explanation is also given over here. The demagnetizing winding is tightly coupled with the primary winding and has the same number of turns as the primary winding. Therefore, when the switch is off, the diode D is conducting the voltage across the demagnetizing winding that is equal to voltage induced across the primary winding, right? The polarity of the voltage induced in the primary winding can be inferred from the dot convention, and we can concur that the polarity of the voltage induced in the primary winding is negative at the dotted end and positive at the non-dotted end when the switch is not conducting. Therefore, the voltage is V in plus V induced. Okay. So you see that this is the voltage across the tertiary winding or the demagnetizing winding. That is, when this diode is on, when the diode is on, the voltage is going to be 72 volts again. Correct? So let me erase this. Yeah. So the voltage is going to be 72 volts over here when this diode is conducting, when this diode is on. So this diode will be on obviously when the switch is off, correct? So what you get is across the primary, this voltage gets reflected, correct? So since the turns ratio is 1:1 directly, 72 volts is again going to appear across this, and that is again 72 volts. Therefore, the total voltage will be 72 and again a 72 volts over here. Therefore, 144. Okay. So is this clear how it is 144 volts? That is, we derived it from the, let me erase the, yeah. So that it has been derived from the tertiary winding. That is, in the tertiary winding, you understand that when this diode is on, right? When the diode is on, the voltage across this winding is going to be directly 72 volts. And this is kind of going to appear, this is kind of going to appear across your primary winding. And again, this will be 72 volts. Okay. So the polarity will be something like this. Therefore, VQ is equal to what? 72 minus of minus 72. That is 72 plus 72. That is 144 volts. Okay. That is why we generally tell when the switch is used in a demagnetizing winding for lossless flux reset topology. So the blocking voltage that you get VQ is equal to 2 times V in. Okay, that is 144 volts. Got it? Another straightforward answer. So the bigger answer would be that you know what is V naught and then you find out what is N, you transfer it to the primary side and then you get what is VQ. But the easier answer is directly 2 times Vn. You, even if you do by this method, that is you transfer N, that is the secondary side to the primary side with by finding out what is N using the given data, and then you'd find out also you'll again get the VQ is equal to 2 times Vn. Okay. Okay. So we'll just go ahead to the next question. What is the resistance value in kilo ohms required for the freewheeling action of the magnetizing inductance to maintain a time constant tau of 0.25 ts seconds during the offstate in the circuit depicted below, where ts represents the switching time with a value of 50 microseconds. So everything is given, that is the output voltage, output load, and then the input voltage and the magnetizing inductance Lm is also given. And they have given that the time constant tau is 0.25 ts. Okay. And ts is 50 microsecond, therefore tau is also given. What is the resistance value required? Okay. So this is again a pretty straightforward problem. That is, okay. So you know that since the turns ratio has been given as 1:1 in the problem. V naught is equal to this, a forward converter, right? So this is a forward converter. You know that V naught is equal to what? V naught is equal to ND V in. N is 1 over here, therefore V naught is equal to dV in, or D is equal to V naught over V in. That is, V naught is 24 and V in is 48, therefore D is 0.5. Correct? So that is what D is 0.5. Okay. Right. So you know that D is 0.5, and when the switch is on, that is when this device is on, right? When the device is on, voltage appearing across the primary winding is obviously equal to the input voltage, which is 48 volts. Okay. Therefore, since the voltage is 48 volts, you know that VL is equal to L di by dt. Therefore, VL is equal to V in. V in is equal to LP into di by dt. Di is delta I and dt is during the capital DTS period. Okay. From this, you get what is delta I. Okay, that is V is equal to L di by dt. From that, you get what is delta I. You know what is D, you know what is delta I, and now we just go back to the given relations. That is, time constant is 0.25 ts, right? That is, tau is given as, you find it out as 12.5 micro, and therefore your tau is equal to LP by R. R is LP by tau. Tau is determined. LP is also given. You know what is R. Okay. So this question, just if you have to find out what is the resistance value, it is straightforward that tau is equal to L by R. So L is given, tau is given, therefore you can find out what is R. The other parts of the problem were done, that is what is D and what is delta I. That those were actually subsections that the question is not asked. I mean, the question is not asked, but anyway, you will know, you know how to find out what is delta I if they ask about the current ripple. But anyway, the question was just regarding what is the resistance. Therefore, this is a straightforward. Tau is equal to L by R, and the time constant is 12.5 microseconds. So from that, you find out what is R, right? Okay. In the problem itself, it is given tau is 0.25 ts. Okay. Okay. So I think this is pretty straightforward. That is tau is equal to L by R relation. We will, if there is any doubt, there is no doubt. We can move on to the next problem now. Okay. So it's a continuation. In the scenario described in question 11, what is the peak voltage dropped by the switch in the circuit? Okay, so there is a forward converter, as you know. What is the voltage? That is, what is VQ? Okay. So when the device is off, you need to find out what is VQ. Okay. So you know that when the device is off, the voltage is going to be Vin, and then Vin minus Vp. That is the voltage appearing across a primary winding. Correct? Or you can also write V in minus whatever is the drop across. So the inductor is going to freewheel something like this. So whatever is the drop across the diode and whatever is the drop across the resistor R. So Vin minus Vd minus Im, that is the inductor current, into R, right? So the blocking voltage can be written as Vin minus Vd minus Im into R, correct? So this is the voltage. Okay. So if you consider the polarity, it will be plus. Okay. Vn plus Vd plus Im into R. Correct? Is this good? That is the switch voltage will be. Let me erase unnecessary ink. Yeah. So switch voltage can be determined by from this loop. That is, this is the loop. Okay. So VQ is equal to V in minus or plus I into R plus V diode. They have not given anything regarding the diode in the problem, I guess. Yeah, but they have given what is, but you know what is R now from the previous problem, that is tau is equal to L by R. You know what is R. So from that you can find out what is VQ. Okay. So at the instant when the switch is turned off, the magnetizing current is at its peak, that is 12 milliamperes. Why is it 12 milliamperes? We just found out from delta I, that is V is equal to L di by dt. Therefore, from this relation you get what is delta I, correct? That is during the dTs period, LP into delta I by dTs is equal to V in, correct? So from this you get what is delta I, that is 12 milliamperes. That is 12 milliamperes. Okay. So you know what is I, since you know what is R as well. R is 8 kilo ohms. That is what we obtained in the previous problem. Therefore, I into R drop is 96 volts. Therefore, the total voltage is going to be B in plus I into R. Diode drop is neglected. Therefore, 48 is the V in and I into R that we just calculated is 12 milliampere into 8 kilo ohm. Okay, that is 144 volts. Fine. Again, very simple. So R, how did we obtain R? So R was obtained from tau is equal to L by R. Okay. And how did we obtain I? I was obtained from V is equal to L into delta I by dTs. V in is equal to L into delta I by dTs. Therefore, what is delta I? So we found out what is I. We know what is R. So you know what is the I into R drop. Correct. Now the total switch voltage by KVL. This is just by KVL, right? V in plus I into R. Correct. Simple, right? That is tau is equal to L by R relation and V is equal to L dA by dt relation. You get what is I into R drop, you know. Therefore, V is equal to V in plus I into R. Okay, and it turns out to be 144 volts. Again, simple, right? If you have any doubts, please write in the chat box. Okay, I'll just check. Okay. Okay, so just give me a second. I will have some water and then we can continue. Yeah, thanks for hanging around. Okay, so we'll move on to the next problem. A forward converter, primary and demagnetizing winding have 50 turns each. Okay, the 250 volt DC input to the converter has plus minus 20% tolerance. The output is regulated to 12 volts through closed loop. So V naught is always 12 volts. Input is 250 plus or minus 20% of that, and the NP and ND are given as 50-50. The converter is operating at 25 kilohertz switching frequency. What is the minimum possible value of secondary turns for feasible operation? Okay, so point is just jot down what is given. That is, you have V in as 250, correct? And then your 250 plus or minus 20% of that. Okay, V naught is always kept at 12. Okay, you don't know what is NS, that is the secondary side windings, but you do know that the relation is V naught over V in, or yeah, or I can write it as let me erase this. So V naught can be written as N into, or yeah, N into D into V in. Correct. Question is what is N, or N can be written as N is equal to NS by NP. Okay, where N is equal to NS by NP. So question is what is the minimum number of N required for feasible operation? Okay, so V naught is always 12. 12 is equal to N into D into V in. Okay, fine. Um, okay, so one thing that you know is for proper flux reset, correct? For proper flux reset, your D cannot exceed 0.5, correct? Your D cannot exceed 0.5 for proper flux reset. Therefore, your D max is 0.5. Okay. So now the question is, what is the minimum value of N that you require? Or I can write it, N is equal to 12 divided by 0.5 into V in, or 24 by V in. Okay. If you want N minimum, right? So then what should be V in? So you need to substitute that particular value of V in, which will make this possible. Okay, so you can either try out for both extremities and see where you are getting the N minimum, or you obviously know that V should be maximum. Okay, so for proper flux reset, you know that Dmax should not exceed 0.5, correct? So from the minimum input, that is plus or minus 20%, that is with minimum input itself, that is with 200 volts, you should be able to generate 12 volts. This is a buck converter, right? That is V naught is proportional to V in. So with minimum voltage also, you should be able to generate 12 volts. Okay. So with this assumption, or with this idea, you get that N minimum into D max, correct? That is V naught by Vn is equal to N into D. Okay. So if you have minimum V in here, V in minimum, and obviously D max, then what is the N minimum that you require? That is a problem. Okay. So from this itself, you can see that V needs to be minimum over here, and obviously D is maximum at 0.5. So you just need to solve for what is N minimum. Okay. So if you are able to see that 12 volts is being generated from minimum, from V in minimum at D maximum, that is at 0.5 duty, you are able to generate 12 volts with minimal V in. Obviously, you will be able to generate 12 volts with other higher values of V in, correct? It can easily be generated at V in max also. So if you are able to generate 12 volts from 200 volts, then obviously you can generate 12 volt from whatever 200 or more than 200 volts. That is the idea. Okay, or you can just solve for both extreme cases and find out what should be N. However, you understand that for proper flux reset, D should be maximum limited to 0.5. It cannot go more than 0.5. D more than 0.5 is not permitted. Okay, therefore D should be kept at 0.5. With D equal to 0.5, you find out what should be N. What should be the minimum value of N so that you're able to generate 12 volts. Okay, you are given extreme values for Vn, that is plus or minus 20%. You can substitute both these values and find out where N is minimal. Or by logic, you will understand that you need to have minimum this much value of N so that the criteria is satisfied at the other extreme also. Okay, fine. Okay, so refer to question number 13. The minimum voltage rating of the switch to be used in the forward converter can be greater than or equal to dash 250, 300, 500, 650. So again, you can draw the circuit diagram. Okay, so you draw the circuit diagram. Here, you neglect this. Let's say NP is to NS is to ND. Okay, so what is the switch voltage? So since your NP and ND are different, again we go to the same logic that we applied some time back. That is, when your switch is off, right? When this device is off, then obviously your switch voltage is equal to V in minus VP, correct? This is your VP, correct? This is your VP. So obviously switch voltage is V in minus VP. What is VP? So VP can be transferred voltage of demagnetizing winding, correct? VP can be the transferred voltage of demagnetizing winding. Okay, and so let me call this as VD. When the diode is on, you know that VD is equal to V in. When the diode is on, VD is equal to V in. Okay, so you transfer it to the primary side, correct? So when you transfer it to the primary side, V primary becomes what? Minus V in divided by whatever is the turns ratio. So minus V in divided by ND by NP, correct? Whatever, this is the turns ratio between demagnetizing to primary winding. So this is your V primary voltage. So you just substitute it back over here. That is, this is going to be what? V in minus or V in plus V in into ND by ND. Okay. So from this you can find out. So again, then it's a straightforward problem. So all data is given in the problem itself. Okay. And since they are asking the switch, what is the maximum, what is the minimum voltage rating of the device? That is, the device should be rated for at least this much voltage. So obviously you need to take the tolerance into consideration, that is plus or minus 20%, right? So considering that 250 into 1.2, right? Including the tolerance, correct? That is why 250 into 1.2 is V in, and NP by ND into V in into this tolerance of 1.2. So it turns out to be 600 volts. Okay. Okay. So we'll move on to the next problem, which is the incorrect statement about forward converter. It's an isolated DC-DC converter. It's a buck-boost derived isolated DC-DC converter. Obviously false. Forward is direct from buck. So this is incorrect. It requires core flux resetting power to increase the switching stress. the leakage inductance related problems can be encountered using dual switch forward converter. Okay, so dual switch forward converter is for core flux resetting, not for leakage inductance. So it's for core flux reset. So this is not the answer. And of course, the it's an isolated DC-DC converter. So this is not the answer. I'm sorry. So leakage inductance related problems can be, yeah, okay. This is the answer. Okay. Okay, so we will move on to the last problem for the day. That is, a forward converter is delivering 25 watts of power and the specifications are given. The peak current flowing through the primary of the forward converter. So what is IP? Okay. So this is the question. So you will know that simply IP is going to be whatever is your IL max, that is this current, divided by N reflected to the primary side. So you just need to find out what is IL max. Correct? So IL max is simply what? It is in the output side. I naught plus delta IL over 2 if delta IL is a peak to peak ripple. So this is the maximum inductor current. And if you reflect it back to the primary side divided by N, this is your IP max. Simple, right? So all specifications are given. Okay. So the power is given as 25 watts and V naught is given. Okay. And R is given, right? 100 ohms. Therefore, from that, you know what is V naught. V naught is 50 volts. Okay. So since for forward converter, V naught is equal to NdVin, D is 0.25. Okay. D is 0.25 and I naught is equal to P naught by V naught 0.5 amperes. So I naught is equal to, this is equal to your average inductor current IL, correct? So your ID peak, ID1 peak is what? IL peak, that is I naught plus delta IL by 2, right? Delta IL is given. So I naught plus delta IL by 2 turns out to be this much, and load reflected to the primary side is going to be N into this value, correct? That is, current gets multiplied if you reflect it back to the primary. Therefore, N into ID peak, that is 1.05 amperes. Okay, you know what is N and found out what is I peak, right? Okay. Okay. So question is, this is the load reflected part through the primary. Okay. But there is one more component, that is the magnetizing inductance current also has a peak. Correct? That is, you know, V is equal to L di by dt. So Vm is equal to Lm into delta I divided by dTs. Okay. Therefore, I is equal to what? Vm into dTs divided by Lm. Okay, that is what is done. Vm is obviously V in. So you can just calculate what is the magnetizing inductance component. That is 0.5 amperes. Therefore, IP is going to be the summation of both. Correct? That is 1.05 plus 0.5, 1.55 amps. You know that even though it is not given in the problem, there is obviously a magnetizing inductance. Correct? So IP is equal to what? IP is equal to this current plus this current. Okay. So it is a summation of both. That is the reflected current plus your magnetizing inductance current. Okay. And we will come on to the last question for the day. Power consumed by the core flux. What is the power? Again, it was solved in the lecture slides. That is half Li square is the energy. If you multiply with the frequency, you get what is the power. Correct? So yeah, half into Lm into Im square into Fs. You just found out what is Im, that is 0.5 amperes. So just solve it, you get what is the power. Okay. Yeah. So this concludes the presentation for the day. Of course, all of these problems will be uploaded in the drive. You can go ahead and have a look, especially the last few problems wherein we were just a little bit short of time and we just had to quickly go through the problems. So yeah, please do go over the problems, and if you have any doubts, you can of course ask in the next week, or you can just post it in the Google group as well. So yeah, so thanks for attending today's session. If you have any doubts, this is the right time to ask, or else we can close for the day. So I think we have seen quite a few problems on forward and flyback converters. Please do go over the problems. So yeah, I think this should help you in solving the assignment solutions. So if you have any doubts, please do write in the chat box, or else we can close for the day. So I will first stop sharing. Yeah, so okay, so thank you everyone for attending. Have a great week ahead, and yeah, good night. I'll just leave. Bye.